Hey, Calc students, this is Mr. Beck. Today we're going to be talking about two separate topics, which are actually very connected. The first topic is sequences. Now, this is going to be a little bit of a pre-calc review for some of you, but that's okay. When it comes to a sequence usually comes from a certain rule, and that certain rule, typically, we're going to give a name. In this case, we're going to be using a sub n quite a bit for the rule, which should match up with what you did in pre-calculus as well. And then what we're going to do with that sequence is we're going to add the terms of the sequence, and that's where we're going to get a series. And that's topic number 2, where we'll be talking about the series and finding the sum of an infinite series, maybe. And that's really going to be the overall theme of Chapter 8, which we're going to be looking at a series of numbers and trying to determine if the series converge or diverge. And we're going to begin with that discussion today. So without further ado, if you notice, what you're seeing here is a graphical representation of what's going on with the limit. And limit plus epsilon and limit minus epsilon means there's probably a limit definition that could be used on here. And there is, and sadly, we're not going to really get into it. But what we're talking about the limit of a sequence is what happens when you're finding term after term after term, whether you're applying or usually applying the rule. So eventually, we hope or we expect that it's going to reach a certain value. And if that reaches a certain value, that's what happens at infinity, which is our tie-in to 7.7, where we found infinite limits. And we're probably going to be using L'Hopital's rule quite a bit, which is one of the reasons why 7.7 and 7.8 really are combined together in this Chapter 8 unit, because we are going to be working with infinite limits. So without further ado, if the limit of the sequence is L, then the limit as n approaches infinity, a base of n will equal L, and that's for every epsilon. Again, there's something more formal. You should recognize that this is kind of connected to the formal definition of mathematics, or in mathematics for the limit. I'm not going to get into that, again, sadly. So if the limit exists, then the sequence has to converge to a certain number. If the limit does not exist, then the sequence diverges. That's going to be a very happy thing to say is if we have an overall limit at infinity, then the sequence can converge. If the limit does not exist, and that does not exist usually has to do with infinity, then we're going to say that the sequence diverges. And again, this is all setting this up for what happens with a series. So problem number 1, find the limit of the sequences. So we should see a little bit of a connection to maybe some of the stuff we did in Chapter 1 as well as Chapter 7 or Section 1.7. So the limit as n approaches infinity of a sub n is going to be the limit. If you remember in a problem like this, what we have is the square root of n squared. If we have the square root of n squared, we have to take the absolute value of n. Now, the absolute value of n, if n approaches infinity, is just going to be n itself. So these reduce, and then our limit, when we take as n approaches infinity, we'll have 5 over the square root of 1 plus 4 over n squared. And we know that limit, this limit specifically is 0. So that gives us the overall answer of 5. If the limit of a sequence is a certain number, meaning it exists, then that sequence has to converge. For part B, we will take a look at this. Idea is we have -7 to the negative n power. So let me be a little bit more formal with this one because I think I kind of jumped over it. So let's walk through it. We'll say this is the limit as n approaches infinity. I will write this as the negative of 1 over 7 to the nth power, which if we take 7 to the infinite power, that's going to be a really, really large number. So it's going to be 1 over a really, really large number. Now, please don't ever write 1 over infinity. I think it's a great mentality to have, but don't ever write it because bad things are actually going to happen. So I'm going to just say that it's overall 0 because the denominator gets significantly bigger than the numerator, especially since the numerator is constant. Therefore, since we have an overall limit, then our sequence converges. The third one, the limit as n approaches infinity. We have the sine of pi times n over n squared. Now, in a situation like this, the sine function is not going to grow anywhere. It's not going to grow in any way bigger than 1 or smaller than -1. So what's happening here is this is a fixed number. This is a fixed number between 1, -1, and 1. Because that's a fixed number over an infinitely large number, that's why our overall limit is 0. So our sequence is going to converge. For part D, if we take a situation like this, the numerator is going to be bigger than the denominator. And the question I have is, why is that true? For some people, it's like, okay, that's obvious. For some people, it's not. So let's kind of walk through it just a little bit. And I'm going to say, if I have a limit that looks like this, one of the things that I can do with this, because this is really infinity over infinity, right? Because this is infinity over infinity, we can apply L'Hopital's rule if we really want to. We could do some algebraic manipulation. That's the beauty, that we have lots of different ways that we can approach this problem. One of the algebraic manipulations that I want to talk about, so limits and approaches to infinity, let me go ahead and make that a little less thick. We could write this as 2 to the 2n over 2 cubed, all divided by 3 to the n times 3 squared. So again, algebraically, now this is not fully required because some people can see exactly what's happening early. If I take this, this will be 2 to the 2n over, so 2 to the 2n, let me write that properly, 2 to the 2n over 3 to the n. Now this will be times 1 over 2 cubed times 3 squared. So how do we know what this number is? The limit as n approaches infinity. We could write this as 4 to the n over 3 to the n times 1 over, what is that, 8 times 9, so 72. I'm not as worried as much about the 1 over 72 as I'm worried about the 4/3 to the nth power. So the limit as n approaches infinity, 4/3 to the nth power times 1 over 72. 4/3 when we get bigger and bigger and bigger. If you remember, this number is bigger than 1 because this number is bigger than 1. A little bit of pre-calc review as well as some of the stuff that we've done. Therefore, that's infinity, which is why our sequence diverges. Moving right along. Our goal is to determine a convergence or divergence. In order for us to determine convergence or divergence of the sequence, we need to really then find the limit. So in a situation like this is a very, very unique situation where, and this happens quite a bit, honestly, when you want to talk about technical computing. Sometimes we want to end up with a 0 in a lot of cases, which 0 in computing, if you know, means false. And then we have an answer if it's going to be true, so a different answer. So these kind of functions work really, really well when it comes to computing. So in a situation like this, if we write out term by term, which is what you see that I did, our first term was 0, second term 1/2, third term is 0, fourth term is 1/8. And by the way, I recommend if you're not seeing some things right from the very beginning, write it out. Because the more you write out, the bigger perspective you have and the more you're going to understand overall. So what I did was I rewrote this to be something that makes sense. If n is an odd number, we have 0, which hopefully makes sense. If n is an even number, we go from 1/2 to 1/8 to 1/18. So we could rewrite that as 2 over n squared. Honestly, we could find that algebraically as well, because if n is even, then our numerator is 1 plus 1. So it's going to be 1 plus 1, because -1 to an even power is 1, so 2 over n squared. Moving right along. So it's either going to be 0 or 2 over n squared. Now we will take the limit, and we have to take the limit of each case because we broke this into a piecewise function. So if n is odd, that limit is 0 because it's a definite 0. If n is even, that overall limit as n approaches infinity is also 0. Because both are 0, we now have convergence for any n. Problem number 3, situation like that, a little bit of beginning work with factorials, and we're going to see this factorial work quite a bit. When you have factorials, like n minus 2 factorial over n factorial, what happens is we're going to break that n factorial into n times n minus 1, and we can keep going after this, but this is n minus 2, n minus 3, n minus 4, etc., etc. But the overall goal is we are going to have that numerator simplify with the denominator. So we have the limit right here. Now, to put the limit as n approaches infinity of a sub n, that limit 0, because the limit exists, we have a converging series. Problem number 4, same kind of idea. So if we take n plus 1 factorial over n factorial, we're going to break that n plus 1 factorial into n plus 1 times n minus 1 times n minus 2 times n minus 3, et cetera, et cetera. But we typically will stop where we have the other factorial that are the same. Those reduce. So now we have the limit as n approaches infinity of, really, it's just n plus 1, which that limit is going to be infinity. Since the limit does not exist, we have a diverging sequence. Well, what happens in a situation like this? In a situation like this, where we have negative 1 to the n power, we are always going to have an alternating pattern. And you can see I sort of drew out this alternating pattern right here, where the first term, really the first term should have been negative. So let's put the first term down here. Second term is positive, third term is negative. But what we're hoping for in this situation, what we're seeing happening is that that limit tends to approach 0. Now, how can we be certain? And this is where we're going to have sort of a powerful idea. It does make sense though, that if we take the absolute value of that function, what that does is that takes the negative out of consideration. So we don't have to worry about the negative. And again, this is going to be a beginning theme through the rest of chapter 8. We don't have to worry about that negative. We could just figure out what is the limit as of the predominant, or really the dominant function that's occurring, 1 over n squared. So 1 over infinity, in essence, is going to be a 0. So our overall limit is 0. And that's, again, the absolute value theorem, that if the limit of the absolute value is 0, then the limit of the overall rule is 0 as well. All right, that's the main stuff from 8.1 that I want to talk about. You'll see there are a lot of like individual small skills used. Again, many of you learn these kind of skills in pre-calculus, which is completely fine. This is kind of our beginning way of just some of the major ideas that we're going to see in chapter 8 when we talk about all of our series. Speaking of series, that's what 8.2 is about. 8.2 covers series and convergence and divergence of the series. So, without further ado, our goal is to determine if a series converges or diverges, and if it does converge, what does it converge to? So this time we're not talking about just an individual rule converging to a number. We're talking about an overall sum that's converging to a number. And just to give you a little hint of where we're going with this, if you take the integral from 1 to infinity of 1 over x dx, this is going to diverge. If we take the integral from 1 to infinity of 1 over x squared dx, this will actually converge. In both cases, what we're doing is we are adding an infinite number of terms, or really we're adding an infinite area. But the idea under the first one, or for the first one, is the area that we're going to be adding here is big enough that it's going to continually get a bigger and bigger and bigger value, where the 1 over x squared model is small enough that whenever we add our terms, or whenever we add, and I'm going to say Riemann sums here because that's modeling, in the first case, we have a series of Riemann sums that we can approximate with that's always going to be a countable area. Where in the second one, what happens is these will get continually smaller and smaller, so eventually it's not going to be very countable. So in the first case where it's countable, that's where we have the divergence of the series. Second case where it's not countable is where we have convergence of the series. I think I might have said that backwards. The top one is not countable, the bottom one is countable. But anyway, hopefully you understand. So when we take a look at the sums, one of the things we're going to do is we're going to be talking about partial sums, because if we could find the sum up to a certain extent, mainly in a situation like this, where if I find the sum up to there, that's going to be more important because everything after that is virtually nothing that we're adding on. So with our partial sum, we're going to say our partial sum, or nth partial sum, is going to be the sum of the first through nth terms. So it's the sum of the first through the nth terms. Now, if the sequence of partial sum converges, then the overall series is going to converge. And if that partial sum diverges, then the series will diverge. So that's where, in a case like what I kind of described here, because I'm always adding something countable, that's where the divergence is occurring. Where in the bottom case, everything added up to here is really the countable part. Everything after that is virtually nothing. So we can continue to count here, which is where we have divergence, where here we are just going to add basically nothing each time, so we have convergence. So that's the main idea. So again, some skill-based stuff. Find the first 5 terms of the sequence of partial sums. So the first 5 terms, if we plug in 1, plug in 2, plug in 3, plug in 4, plug in 5. So we have those 5 terms. So this is what we call the 5th partial sum. So the sum of those 5 terms, because what's happening is we're getting a much smaller and smaller value each time. That's where we know our series is going to overall converge. So as you look term by term, you see that that value is getting smaller and smaller. And yes, they are alternating signs, but it kind of goes back that when we're adding, so as we're adding number or adding these terms, the sum will get bigger and then eventually converge to an actual value. So problem number 2, 1 over 2 to the nth power. What we have here is we're going to take the infinite sum, so 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16. And I'm not sure if you guys know this pattern, but let's talk about it a little bit. So the first sum, if we write out the sum, the partial sums, first sum is 1/2. 1/2 plus 1/4 is 3/4. 3/4 plus 1/8 is 7/8. And one of the things that you're going to want to see is this is going to be 1/2 plus 1/4, which is 2/4 plus 1/4, which is where you get the 3/4. 3/4 is 6/8. 6/8 plus 1/8 is 7/8. 7/8 is 14/16. 14/16 plus 1/16 is 15/16. So what you're hopefully seeing in a situation like this is we are getting really, really close to the overall value of 1. The overall value of 1, because the numerator is always going to be 1 unit smaller than the denominator. Basically, that sum ends up being n over n plus 1. How about n minus 1 over n? Not directly related to that n, but anyway, but we're going to get a number infinity minus 1 over infinity, which is going to be a number really, really close to 1. Now, some of you might be saying, hey, I've seen these kind of things before. This is a geometric sum. Because it's a geometric sum, we could use the rule for geometric sums, which would be the first term times r to the nth over 1 minus r. There's a really, really cool proof of that I would like to show you, but I'm not going to because this video is going to be long enough anyway. Now, this only occurs for where the absolute value of that ratio is less than 1. Because our ratio here is 1/2, and one of the ways we could see that is we could write this as 1/2 to the nth power. Since our ratio is 1/2, it is less than 1, and we can use the overall sum. That overall sum is going, in this case, the infinite sum, if you will, is going to be 1 times our ratio of 1/2 to the nth power. So 1/2 to the infinity power over 1 minus 1/2. So 1/2 to the infinity power over 1 minus 1/2 is going to be basically 1 times, I really should have done this one in advance. So it ends up being 1 times, well, let me just say 1. Awkward moment. Okay, let's work with it. So maybe I shouldn't have shown that to you. All right, teachers make mistakes too. So then we have a situation like this, where once again, when I'm trying to figure out what this limit is, if I want to find this limit, one of the things I could do is combine these algebraically. So I could write this as n plus 1 minus n over n times n plus 1, and we could work with it in that case. But what I like about this situation is it shows what we call a telescoping series. Now, a telescoping series is where when you plug in your terms, what you're going to see is you have 1 minus 1/2, and that would be your first term. Your second term is 1/2 minus 1/3. Third term is 1/3 minus 1/4. So what you're seeing happening is the 1/2 and the 1/2 here are going to cancel. The negative 1/3 and the 1/3 here are going to cancel. Negative 1/4 and the 1/4 there are going to cancel. So what ends up happening is you're going to always have that first term of 1 minus 1 over whatever n plus 1 is. So in a situation like this, what happens when you take the limit as n approaches infinity of 1 minus 1 over n plus 1? You're going to get, in essence, 1 minus 0, which is 1. Because this limit is 1, we do have a converging series. And that converging series is, our limit is over 1. So if the limit converges, then the series is going to converge as well. All right, and now let's actually talk about this telescoping series. So the telescoping series is of the form that I just showed you, b minus b2 plus b2 minus b3, b3 minus b4. So the nth partial sum is going to be the first term. So first term minus the second portion of the last term. So, and the series will converge if b sub n, or really that last one, approaches a finite number as n approaches infinity. So that's kind of what I just showed you right up there. So let's go ahead and find the sum of this overall series. Now in a situation like this, we're going to bring back something which is a BC topic only, where it's partial fractions. So partial fractions, we turn 4 over 4n squared minus 1, sorry, 2 over 4n squared minus 1 into its partial fractions. And if you remember that, just a quick skill review. A over the first factor plus b over the second factor, and then we figure out what a and b are. So what I did was, using partial fractions, I turned what we have there into a situation that looks like this. Now, a situation that looks like this, a lot of people recognize, and this happens a lot with the difference of squares, but a lot of people recognize that's really a lot of telescoping series. So when it comes to telescoping series, how do you actually recognize it? Honestly, just start plugging in values, you guys. Plugging in values gives you that numerical aspect, and numerical aspect is what allows you to see the greater picture. And that greater picture is more the algebraic and the graphical. So negative 1/3 plus 1, negative 1/5 plus a third, negative 1/7 plus a fifth. What ends up happening is this term here cancels out with that term. The negative 1/5 and the positive 1/5, the negative 1/7 and the positive 1/7. It would actually look a little bit more like what we're seeing up here, where these two are going to cancel out if I had rearranged the order. But anyway, our sum, and that is our infinite sum, is 1 minus the limit as n approaches infinity of 1 over 2n plus 1. And again, it's because it's that term. So anyway, you can see I rewrote it down here, and that overall limit is going to be 1. Therefore, there's our sum. Our sum is the first term that comes out of it minus the overall limit of the second term. And then we get geometric series. So you think I sort of prompted some of these ideas. That example 2 up here was geometric, example 3 was telescoping. That's because they're going to be more or important enough that we're going to reference them over and over and over again. Especially when it comes to geometric series, we are going to use geometric series in a lot of different ways throughout the course of the next couple sections. So then we're going to take, I'm getting ahead of myself. Back to the problem. So find the overall sum of the geometric series. So something that we need to know about geometric series, and I mentioned it earlier, that if our ratio is bigger than 1 or smaller than -1, then our geometric series is going to diverge. We could see that, suppose we have 2 to the nth power. 2 to the nth power is going to be 2 plus 4 plus 8 plus 16. We're getting bigger, bigger, bigger. Because this is getting bigger each and every time, you know that we're going to have divergence. The last one, or the problem that I had up there, was I had 4/3 to the nth power. So that'd be 4/3 plus 16/9 plus 64/27. Notice that number is getting bigger than 1 each time. Because we're getting a larger and larger number each time, then we're going to have divergence. And I'm sort of referencing if we're going to be adding numbers above 1 and between 0 and 1. That's going to be an important idea. And again, it shows with the ratio even, that if the ratio is between 0 and 1, then if the absolute value of the ratio is between 0 and 1, we should have convergence. And that's because if we add a number smaller than 1 each time, we are going to eventually add up to 0. Now, in some situations, it's still not very countable, and that's the 1 over n situation that I mentioned earlier. Some of you are probably going, I know where Mr. Beck's heading with this one, but if we start adding a number bigger than 1 each time, we're always going to get bigger and bigger and bigger. And that's exponential growth, guys. So, to find the sum of the geometric series, what I did here was I went ahead and took out the 3, and I said, okay, what's the sum of that series? Sum of that series, I did use the rule, first term over 1 minus the ratio. So the first term is going to be what happens when n equals, in this case, 0. Everybody, that number is going to be important. So our first term is 3 times 1/2 to the 0, which is 3. And you see I started writing out some of those series right there, or partial sums. So the first term over 1 minus the ratio, which gives me 6. Therefore, my sum converges to 6. The second case, it's kind of funny if you take a look at the second case and you try to apply the 1 over 1 minus r, you get -2. And this is one of those that I know we talked about a little bit, that the sum of all the infinite numbers was -1/12. Or sorry, the sum of all the positive integers is -1/12. This is kind of a situation like that where algebraically we can manipulate it to get there. We know in reality we can't, although I say reality, when it comes to complex numbers, we can show why that's true. There's a video that I began to show to some of my students about that. Fascinating, absolutely. So anyway, because our sum ends up being, because our ratio is bigger than 1, then this overall sum is going to diverge. Now, whenever you say divergence, you can't just say diverges and you're done. You always have to have some kind of justification. You know this is calculus class. You have to justify what you do, why you do, and how you do it. So the reason why it diverges is the ratio is bigger than 1. The limit of the nth term. So next big idea, limit of the nth term of a convergent series. If we know that an overall series is going to converge, then the limit of that rule, or the limit of that sequence, has to be 0. Because eventually, if you have convergence, you're going to be adding nothing on each time. And I referenced that up here where I was showing you the visual. Eventually, we're going to be adding nothing each time. And because we're adding nothing each time, that's where we're going to have convergence of the overall series. So we know that let's move down, if we have convergence of a series, so if we have convergence of a series, then the overall limit has to be 0. But we have to be careful, because just because the limit of the nth term is 0 doesn't mean we actually converge. And I showed this to you earlier, that this infinite sum of 1 over x actually diverges, even though the limit of that sequence is 0. So the conditional statement here is important. So if the series converges, then the limit of the sequence is 0. But if the limit of the sequence equals 0, anything can happen. When you talk about rules of logic, just because a conditional statement applies doesn't mean it's why can't I think of the word right now? So just because the conditional statement applies doesn't mean its converse actually applies too. So that's where we have the need for more tests. So nice thing is, if we have the limit equaling 0, or if we have convergence, we know the limit has to equal 0. So if the limit does not equal 0, then therefore we have divergence. So we have divergence. So one of the things that we can determine right from the beginning is, does our limit equal 0? And let's kind of like write down like a logic statement. So if the limit equals 0, as n approaches infinity equals 0, and I missed my rule in there. So if the limit of the rule equals 0, it could converge or diverge. So it could converge. Let me just go ahead and write that as C or D. It could converge or diverge But if the limit as n approaches infinity, base of n doesn't equal 0, then we know we have divergence. So that's why we have the nth term test for divergence. So moving right along. Let's take a look at this situation. The sum of 1 over 4 to the n. So first of all, what's the limit as n approaches infinity of 1 over 4 to the n? We know this is 0, so it could converge or diverge. So how do we determine if it converges or diverges? We need some extra information. This is a geometric. Because it's geometric and the ratio is between, the absolute value of the ratio is between 0 and 1. Therefore, we know it's going to converge. In our second case like this, what's going on here? One of the things that I'm prompted to see is this 1 plus something over n to the nth power. Because I have something over n to the nth power, this means there's probably something logarithmic that we could do here. And let's take a throwback to what we did with L'Hopital's rule in 7.7. We said, okay, let's go ahead and set it equal to some variable. And chapter 7, I called that L. Here, I'm not sure why I chose Y, but let's go ahead and choose Y. So when we try to find this overall limit, the natural log of y, this is going to be a kind of a repeat of everything that we did in 7.7. So what ends up happening is our limit is e to the k. Because e to the k does not equal 0, that's why we know we have divergence. And why do we have divergence? It's nice for us to actually write the name of the test. The reason why we have divergence is the nth term test. So this is going to be the beginning of the skills. Now, in a lot of ways, this is going to be an easier section for you to work on. Please, please, please don't rush over these two sections, because this is the essential skills that we're going to be using, and we're going to be using them very, very quickly in 8.3 to 8.6. And so I'm going to say that right now, I want you to have the mentality of why the limit exists or doesn't exist, why the series converges or diverges. Make those connections very, very carefully, because we're going to start going faster and eventually say, oh, by the ratio test, this is happening. By the nth term test, this is happening. So we need to know these foundations really, really well. So this is Mr. Beck signing off. Have an amazing day and weekend, everybody.